All right, let's have a look at going back the other way now, integrating the exponentials. So if we have an exponential to some linear function, then out the front, when we integrate it, we'd end up with 1 over a. I suppose you could think of it as dividing by the derivative, I guess, of the linear function, but don't think like that because it doesn't work if it's not a linear function. So it's just 1 over the coefficient of x e to the ax. That's very limited in how it can be used. I find this idea a bit more useful in that we know that when we differentiate e to the function x, we get the derivative times e to the function x. Therefore, logically, if we integrate the derivative times e to the function x, we must get back to e to the function x. So we want to try and create the derivative out the front. Now, if we can't do that, then we'll have to use other techniques, which we'll see in extension 2. But as far as extension 1 goes, everything should be able to be done this way. So e to the 5x, well, it is a linear function, as I say. So you could simply look at that and say, well, that's 1/5 e to the 5x, 1 over the coefficient of a. But if you did think about it in the other way, what you'd be saying to yourself is, well, it's e to the 5x. I want to create the derivative out the front. So I would like 5e to the 5x. But then to balance it out, I need a 1/5 out the front. And I know 5e to the 5x, well, I must have differentiated e to the 5x to get that. And so again, I get 1/5 e to the 5x. So that's why with a linear function, you can simply go just 1 over the coefficient of x out the front, and that can be a little bit quicker. But see, something like this, where it's not a linear function, I can't do that. Okay? So now I'm looking at it, I'm saying, okay, I want the derivative out the front. Derivative of x squared is not x, it's 2x. So I'll set it up and say, right, let's make it 2x, but I can't change the question. So I need to put a 1/2 out the front to balance it out. And then I know what 2x e to the x squared does. I know that must have been e to the x squared that I differentiated to get 2x e to the x squared. So I've got 1/2 e to the x squared. Over there in example 3, again, this one is a linear function. So I could just go 1/9. Or thinking about it the other way, well, I'd like the derivative out the front. The derivative would be 9, but to balance it out, I put a 9th out the front. So therefore it becomes 1/9 e to the 9x minus 5. The square root of e to the power of x, going to have to change that into index form before I can do anything. So that would be the same as a 1/2 x or x on 2, which again is a linear function when you think about it. It's just that it's a fractional coefficient rather than a whole number. So 1 over 1/2 would be 2. So I know the answer would be 2. But again, if I think about it the other way, I'd say, well, I want the derivative out the front. So that's a 1/2 e to the x on 2. Balance it out, I need 2 out the front. So I get 2e to the x on 2. That's probably good enough for an answer. I just tend to like to write my answers in the way they ask me the question. So they wrote it in surd form. I've given my answer in surd form. All right, well, we don't have a product rule for integration, do you remember? So first thing we need to do here is expand the whole thing out. And remember, e to the x times e to the x, not e to the x squared. E to the 2x minus 2e to the x minus 3. Again, each one of these are linear functions, so I could just go a 1/2 e to the 2x. And, well, e to the x, there's that wonderful thing again. World's easiest derivative, world's easiest integral as well. Differentiate e to the x, you get e to the x. Integrate e to the x, you get e to the x. So that one becomes e to the x. And the 3, of course, becomes 3x. Don't have a quotient rule. So let's do the division first of all. So e to the 5x divided by e to the 2x would be e to the 3x minus e to the minus x. Be very, very careful with your negative signs here. The first one's fine because 1 over the coefficient gives me a 1/3. But the coefficient of x here is -1. So it'll be minus e to the minus x. So that's plus e to the minus x. Let's do a definite integral. In this case, the power is x cubed. So I'd like to see 3x squared out the front, not just x squared. So let's write it as 3x squared, but to balance it out, I'll need a third out the front. So now I know this integral. It'll go to e to the x cubed, and my limits are 0 and 1. Sub 1 in, sub 0 in. Now, whether you write e to the 0 is up to you, I guess, because remember, anything to the power of 0 is, of course, 1. So you might just write 1 down straight away. And, of course, e to the power of 1 is just e. So we've got a third e minus 1. Ooh, 3 to the power of x. So the base is not e. Well, remember when we differentiated, what we said was all we had to do was multiply by the natural log of the base. Well, this is the reverse operation. So all we have to do is divide by the natural log. So this will be 3 to the power of x, because that would be, the world's simplest integral, world's simplest derivative. But because it's not base e, we divide by the natural log of the base, so natural log of 3. Again, just like we saw yesterday with the differentiation, that all comes from the change of base rule, and that's why we end up with that log 3. Okay, a couple of exercises, integration, and all the different applications, finding areas and volumes and what have you.